Hello, this is KiboCUBE Academy, Lecture 18, Introduction to CubeSat Payload System. My name is Masahiko Yamazaki. I am an Associate Professor at the Department of Aerospace Engineering, Nihon University in Japan. I have been studying space deployable structures, especially membrane deployable structures, and also developing small spacecraft. I have worked on CubeSats from a 1U educational CubeSat to a 3U technology demonstration CubeSat. Currently, we are developing 6U satellite for science missions and a hands-on educational satellite kit. Now, let's start the lecture. Here is an overview of this presentation. I will start with an introduction to payloads for CubeSat. Number 2, introduction to CubeSat. Number 3, introduction to CubeSat Systems. Number 4, types of payload systems and examples of CubeSat mission payloads. Finally, I will conclude my presentation. I think it is important to know the overview of a CubeSat and CubeSat systems to develop a payload system. So, let's move on to the first chapter of the lecture. The first chapter is the introduction to payloads for CubeSat. So first of all, we need to understand satellite orbit when we talk about payload systems. There are many different types of satellite orbits. The orbit is determined by several parameters such as altitude, orbital shape, and angle with the equatorial plane. I have illustrated several typical satellite orbits in this figure. The blue one is a geosynchronous orbit. It's also called GEO. The orbit altitude is about 36,000 kilometers. Geostationary satellites are located on this orbit, and they are rotating around the Earth once a day with the same rotational velocity of the Earth. This means a satellite at GEO maintains the same location relative to the Earth. The green one is the sun-synchronous orbit, also known as SSO. An SSO is a kind of polar orbit and flies over the North and South Pole regions. Together with the effect of the Earth's rotation, satellites in SSO have a chance to fly over most of the place on the Earth. Moreover, the sun direction relative to this SSO is constant throughout the year. So you have the same illumination conditions on the observed surface of the Earth. Therefore, this orbit is suitable for Earth observation. The red orbit is the ISS orbit. The orbit is tilted with an inclination angle of about 51.6 degrees. The altitude is about 400 kilometers. Because the orbit altitude is low, the ISS orbit also belongs to low Earth orbit, or also known as a LEO. Satellites released from the ISS will also follow a similar orbit as the ISS. Unlike SSO, the sun illumination condition of the ISS orbit changes with the time, so you need to consider several important effects on your satellite, such as power generation and thermal control. So, a CubeSat orbiting the Earth can cover a wide area on the Earth. CubeSat orbiting in a high inclination orbit can cover a large geographical area. A higher orbit provides a wider field of view, and a lower orbit provides a higher ground resolution. This feature of global accessibility can be utilized for Earth observation, communication, environmental measurement. You can conduct periodic frequent observations of ground areas and the satellite orbit. And you can have communication contact with ground stations in the visible area. And you can measure the space environment, such as magnetic field, radiations, etc. The unique environment provided by space, including microgravity, vacuum, high radiation, ultraviolet radiation, low and high temperatures, and the presence of atomic oxygen and plasma, can be used for a variety of experiments in earth science, material science, bioscience, and medical science. On the previous slide, I talked about the characteristics of space utilization and CubeSat missions capabilities. The payload is a part of the CubeSat system that carry out its mission. The bus is a part of the CubeSat system designed to survive in the space environment. In this slide, you can see the example of 3U CubeSat SQ and 1U CubeSat SEED2. In the case of this 3U CubeSat example, 1U is assigned for the payload instruments. 2U is assigned for the satellite bus system. In the case of the 1U CubeSat example, payloads and bus system are mixed. For educational missions, the CubeSat itself becomes the payload and accomplishes the educational objective. For a payload example, if you want to take image of the Earth, you need an Earth observation camera. If you want to receive ground sensor data and uplink commands, process and send information to ground stations, you need communication instruments. If you want to see how a certain technology behaves in space, you need a component to be an engineering demonstration. These necessary components are the payload. So, the payload is a central element in accomplishing the mission. To design, develop, and operate CubeSat and payloads, it is very important to know the life cycle of the CubeSat. This is a typical mission life cycle of CubeSat. CubeSats have a design and development phase, a launch and orbit insertion phase, and an operation phase. Each phase has different requirements and constraints. These requirements and constraints need to be clarified. For example, during launch, there are vibration, shock, and launch acceleration factors. In orbit, there are conditions such as solar radiation, thermal radiation, and high vacuum. The payload and CubeSat design must freely meet all requirements and constraints across the entire life cycle. Payload is not the only element of CubeSat that make the mission possible. The functions of a satellite system can be categorized into several subsystems to meet all requirements and constraints of the CubeSat lifecycle. They are the power control system, communication system, command and data handling system, structure and mechanism system, thermal control system, attitude control system, orbit control system for advanced missions, and the payload system. This slide attempts to explain the relationship between CubeSat subsystems, which are closely related to each other. I have put the payload system in the middle on the top of all the subsystems. I wanted to emphasize that the payload is representing your satellite mission objectives, and all the subsystems exist to fulfill the required functionalities to achieve the mission objectives with the payload. Also, all subsystems except the payload system are denoted as the satellite bus system, with the payload being the passenger among the other subsystems of the bus. So, it is important to understand the CubeSat life cycle and the CubeSat operational environment in order to identify the requirements and constraints associated with the payload, which will clarify the required functions. So, let's move on to the second part of the lecture, Introduction to CubeSats. A CubeSat must conform to specific criteria that control factors such as its shape, size, and weight. This affects resources such as size and power available for payloads. The specific standards for CubeSats help reduce costs. A 1U CubeSat is a 10 cm cube with a mass of approximately 1 to 1.33 kg. So, a 1U CubeSat is a 10 cm cube. The dimension as a laid direction is a bit longer than 10 cm, as illustrated in this figure. There are several sizes of CubeSat: 1U, 2U, 3U, and 6U, etc. CubeSat come in several sizes, which are based on the standard CubeSat unit. Some standards are available, and I have attached one, the GEM Payload Accommodation Handbook, Volume 8. I think this is the most important and relevant document for you when you apply for launch opportunity throughout KiboCUBE Academy. Among the possible form factors of a CubeSat, the 1U CubeSat in particular is an ideal platform for learning the engineering skills and technology essential for satellite development and operation as a first step. This slide shows the exterior and interior of the 1U and 3U CubeSat, including their components. There are bus subsystems, including a communication subsystem, electrical power supply subsystem, as well as a command and data handling subsystem. There are payloads, sensors, cameras, extendable masts, and a deployable membrane. A smaller format is mainly for fundamental functionalities to survive in space. Large formats are required for missions, which require large sensors and components, accurate attitude control, and a large amount of data transfer. This slide describes the CubeSat Orbit Deployer, one of the elements of the CubeSat system. The deployer is the interface between the CubeSat and Kibo, or the launch vehicle. The deployer provides attachment to Kibo or launch vehicle and released it into orbit at the appropriate time. At the time of release, an electric signal is sent to the CubeSat deployer. The door opens and the CubeSat is released into orbit. Kibo provides options of JSOT in 3 different forms: 3U, long 6U, and wide 6U. The CubeSat Orbit Deployer is configured to meet the CubeSat standard. A CubeSat must conform to specific criteria that control factors such as its shape, size, and weight. Equipment cannot be mounted outside of the CubeSat Orbit Deployer envelope. The electrical power must be turned off before orbit insertion and turned on after insertion by a release detection switch. These constraints affect the size, weight, shape, and operation of the payload. As I mentioned in the previous slide, the size, weight, and shape constraints affect the size, weight, and shape of the payload. All CubeSat components must be entirely within the envelope. So, for example, Prelude, a 6U CubeSat, has its bus and payload stored as shown in this figure before launch. However, if a hold release mechanism is reinstalled, the solar panels and the sensors with an extension boom can be held before release and deployed after release into orbit, triggered by a signal from the CubeSat. As I mentioned in the previous slide, before the CubeSat is released into orbit, deployable components need to be constrained. For example, deployable solar panels to increase their sun exposure, deployable antenna, or a deployable sensor. The most common method of constraint is to tie a fishing line to the component and pass the other end by a simple resistor such as nickel wire. When a current is applied to the resistor and the resistor heats up sufficiently, the fishing line melts and the deployable structure is released. Hold and release mechanism and the deployable structure are one of one way to change the shape of a CubeSat on orbit while preserving the CubeSat constraints at launch. This slide shows the actual implementation of the antenna deployment system based on the wire mechanism. This is a design example of 3U CubeSat, Origamiat 1. In this example, the antenna is based on convex tape. The two convex tape antennas are wrapped around the satellite structure. The shorter antenna is wrapped first, followed by the longer antenna wrapped on top of it. Then the tip of the longer antenna is restrained with thread and fixed to the satellite body. The threads are burned out with nickel wires in space when the antenna are deployed. Let's move on to the third chapter, Introduction to CubeSat Systems. In the previous slide, we have considered the relationship between CubeSat requirement and constraints. Let us now consider the relationship between CubeSat systems and its payload. First of all, a system is a combination of hardware, software, people, data, service, and many other elements that work together to achieve a goal. A CubeSat system consists of several elements, such as the CubeSat itself, ground stations, operators, ground sensors, etc. And there are interfaces between the components. The interior of the CubeSat is also composed of multiple component elements with interface, each of them, and they all have requirements like this. The payload is one of these internal components, and for a successful mission, it is not enough for the payload to perform well on its own. All of the elements surrounding the payload and their interfaces must work properly. I will say it again and again. The CubeSat system consists of payload and a bus system. The CubeSat bus system can be divided into several subsystems. For example, power control system, communication system, command and data handling system, structure and mechanism system, thermal control system, attitude control system, orbit control system, etc. Payloads do not operate by themselves, but rather demonstrate their capabilities in combination with other onboard hardware, software, and interfaces. As shown in this figure, the proper operation of a CubeSat is not only dependent on the payloads, but also on the proper operation of the other component in the satellite system. Therefore, CubeSat resource, for example, power, space, etc., must be allocated to maintain bus functions for power generation, storage, management, thermal control, communications, such as sending information to Earth, attitude determination and control, and data processing. The power, space, mass, and data available for payloads are limited. This slide shows the relationships of a payload and bus system. The larger the CubeSat is, the more payload instruments can be carried, and the more advanced the missions are that can be conducted. The size of the CubeSat for each mission shall be carefully selected based on the difficulty level of the mission objectives and the complexity of the requirements on the payload instruments. Larger, high-performance bus system will be required for high-level missions. For example, higher power generation, storage, and consumption capabilities, which means large solar panels and more battery capacity, giving higher data processing capability, more memory storage, and high communication throughput, as well as better accuracy in attitude determination and control capability. The larger and the more complex the system is, the more effort will be required for system integration, because the number of elements and the number of interfaces increase. It is recommended that interface between the payload and the bus system is clearly defined and kept as simple as possible, so that they can be developed in parallel. Doing so will shorten the entire development and the verification time schedule. Let's move on to the fourth topic, types of payload systems and example of CubeSat missions. This slide shows example of major CubeSat missions. For example, Earth observation such as optical, hyperspectral, multispectral, panchromatic, etc. Communication such as unidirectional, two-way communication, etc. Meteoroid measurement. Experiments inside a CubeSat such as material experiments. In-situ space environment measurements such as magnetic field, electric field. Technology demonstration such as deployment mechanisms. Advanced technologies such as new sensors, electrodynamic tethers, etc. Today, I'd like to introduce you to 6 of these examples in the following slides. The first example is Earth observation. The satellite is in orbit to observe something that is on Earth. For examples, construction, humidity levels, amount of vegetation, detecting spills into the sea, disasters, etc. Each of these missions requires a different type of camera, specified by resolution and wavelengths. Regarding resolution, the higher the resolution, the more detailed the image, but the larger the size of the camera and the satellite. Regarding wavelengths, there are optical, hyperspectral, multispectral, panchromatic cameras, etc. The difference between them is the type of observation that is made and the wavelength bands of the light you want to capture. This is 1U CubeSat Sci4. It was implemented with an Earth observation camera and 1200 bit per second communication system to capture and downlink Earth photos. The satellite captures as many photos as possible, and only photos which have Earth image were stored and downlinked. 1200 bit per second communication speed requires 3 to 4 days to downlink per photo. Sci4 also include a technology demonstration mission to realize CubeSat bus functions for a certain period. Satellite bus system functioning in itself is a good mission if it is your first project. The second example is a communication mission. The satellite is in orbit to collect data and send data to the Earth. For examples, disaster prediction, water level monitoring, soil moisture, pH, AIS, etc. A system in which small sensors placed in the ocean or on the ground transmit data to the Earth satellite, which orbit the Earth and collect the data sent from the sensors on the ground. Each of these missions requires a different type of communication. For example, unidirectional systems and a two-way communication system, such as send or return message, data, or commands. The next CubeSat example is the signal measurement instrument on the 3U CubeSat. Lesson 3. Receiving and analyzing ground-based AIS, automatic identification system signals from space, is attracting interest. In this case, the receiver and the deployable directional antenna system are the payload. In this example, a 3-axis attitude control is utilized to point the antenna toward the Earth for detecting AIS signals sent from SIP, enabling tracking the position of the SIP with a higher geographical resolution. The third example is the meteoroids measurement mission by the 6U CubeSat payload Delphinus. When a meteoroid with a diameter of several centimeters to several tenths of centimeters impacts the lunar surface, a lunar impact flash is produced in the visible to near-infrared wavelengths range, which can be observed by ground-based telescope as a magnitude 5 to 11, short duration 0.01 to 0.1 seconds flash. In this case, the detection camera for lunar impact phenomena is the payload. This is the 3U CubeSat S-Cube. It was implemented with a meteor observation camera system. A gravity gradient boom was used to point the meteor observation camera towards the Earth's atmosphere for detecting incandescent meteors as they enter the atmosphere. It also had deployable solar panels. The fourth example is that of experiments inside a CubeSat. The satellite is in orbit to use the space environment. The unique environment provided by space, including microgravity, vacuum, high radiation, intense ultraviolet radiation, low and high temperatures, and the presence of atomic oxygen and plasma can be used for a variety of experiments in material science, bioscience, and medical science. This is 6U CubeSat Tenko-2. Tenko-2 plans to do the observation of space environment resistance of advanced space materials. It was implemented with a material experiment unit and in-situ space environment sensor such as high-resolution camera, geospacer observation unit by using a high-energy charged particle detector. The fifth example is in-situ space environment measurement. For example, in-situ plasma, particles, magnetic field, electric field, and atmospheric drag, etc. Observe these physical quantities in situ, where the phenomena are occurring, and clarify the physical processes behind the phenomena. Also, to understand phenomena that occur in places that cannot be visited directly, such as distant celestial bodies and the ionosphere, etc. This is 1U CubeSat Series 2. It was implemented with a temperature sensor, geomagnetic sensor, and digital card. If there is a transmitter near the magnetic sensor, as in a CubeSat, when the transceiver is turned on, high-frequency noise is added to the magnetic sensor. When devices such as a transmitter are placed in a small and limited space like a CubeSat, it is necessary to consider their placement and operation method. For example, turning off the communication equipment when measuring sensors, in consideration of their effect on sensors. Sheet 2 also include a technology demonstration mission to realize CubeSat bus functions for a certain period. As I mentioned in the previous slide, satellite bus system functioning is in itself is a good mission if it is your first project. The next CubeSat example is the electric field intensity measurement from the potential difference between two probes on the 6U CubeSat Prelude. The 6U CubeSat Prelude is aimed at verifying the reduction of radio wave intensity 4 hours before earthquakes by installing only one pair of electric field probes. In this case, the VLF electric field probe, extension boom, and the mission data handling unit as a payload. After reaching orbit, the extension boom and the solar panel are deployed, and the probe is pointed towards Earth using 3-axis attitude control to observe the electric field intensity. During the daytime, a large amount of observation data is downlinked, and during the eclipse, when there is little ionospheric disturbance, the attitude is controlled and the electric field intensity is observed. The sixth example is a technology demonstration. the satellite is in orbit to see how a certain technology behaves in space, such as a new sensor, communication instrument, structure, power-generated instruments, etc. The next example is orbit demonstration of a thin film deployment mechanism. This example is a 1U CubeSat Freedom. The payload was the deorbit state for fast deorbiting and re-entry into Earth's atmosphere from the ISS orbit. This CubeSat had no communication system or solar cells. Freedom demonstrated on-orbit deployment of the thin film-based deorbiting state, which can be utilized for space debris mitigation and prevention using atmospheric drag. The next CubeSat example is a multifunctional deployable membrane structure on the 3U CubeSat Origamiat 1. It deploys a 1 meter by 1 meter membrane in space and obtains data about deployment dynamics and deployed shape. It also measures the performance of thin film device on the membrane, such as thin film solar cells and the thin SMA shape memory alloy antennas. After reaching orbit, the boom is extended to maintain the distance between the camera and the subject. It means the membrane. And later, the membrane structure is deployed. The deployed structure is then separated at a certain altitude, and mission data is downlinked. The last example is the electrodynamic tether. This is a 3U CubeSat LETT. The payload is an electrodynamic tether for deorbiting and re-entry into Earth's atmosphere. A 3-axis attitude control is used to control the satellite attitude during the extension of the electrodynamic tether. The device will be useful for space debris mitigation and prevention in higher altitude orbit, as it can operate independent of atmospheric drag. I hope it has helped you to understand CubeSats and their payloads. Now, I'd like to conclude my lecture. There are constraints related to orbit insertion of CubeSat and payloads. For example, CubeSat standards, size, weight, and shape. It depends on the rocket and the CubeSat deployer. Orbit lifetime. Atmospheric drag can be limiting factor for mission life in low Earth orbit. Vibration, shock, and acceleration associated with orbit insertion. There are system requirements for successful payload operations. For example, electrical interface requirements such as I2C, SPI, UART communication protocol, 5 volt, 3.3 volt power supply, etc. Attitude and determination requirements such as determination accuracy and control accuracy, etc. Configuration, size, shape, and mass requirements. Orbital requirements such as sun-synchronous orbit, etc. It's related to an increased degrees in launch opportunities. Electromagnetic compatibility requirements, etc. CubeSat systems have strong inter-device coupling. Aim for an optimal CubeSat by flexible sharing limited resource, such as power, heat, communication, structure, data, etc., while satisfying various requirements and constraints. As explained so far, the payload on a CubeSat are closely interrelated with other subsystems. For successful payload and CubeSat development, it is important to test as many expected functions as possible before interfacing it with other systems. For example, environmental testing include vibration testing, thermal vacuum testing, shock testing, EMI, EMC testing, and anything else required by the launch vehicle provider is important. Keep the scope small with testing and add components systematically, testing them along the way. It is also useful to test individual subsystems before integrating all components. This allows for early detection of design problems and reduce excessive testing of the entire system. Never assume that a board or subsystem that works well in standalone testing will work well when integrating with other board or subsystems. Pre- and post-test inspections, measurements, and functional demonstrations are important. Tests and simulations ensure that everything works properly before putting it into orbit. For example, structural analysis, attitude and orbit analysis, thermal analysis, electricity analysis, etc. Structural analysis to check whether the structural requirements for payloads are met. Attitude and orbit analysis to check whether the attitude and orbit requirements for the payload are met. Thermal analysis to check whether the thermal requirements for the payload are met. Is a design freely capable of meeting all the requirements and constraints? I have been talking about the same things again and again. The CubeSat payload should be designed with careful consideration of the requirements and constraints emerging from the entire CubeSat system lifecycle. With this, I'd like to finish my lecture today. Thank you very much for your attention.